All right, welcome. If you're getting ready for a big technical exam or a coding interview, we all know those synchronization questions can be real stumpers. So today, we're going to master these tools. We're going to break down the whole thing, from the absolute core problem all the way up to the pro-level stuff. So here's the game plan. We're going to start with the absolute basics. What is the problem we're even trying to fix? Then we'll build our way up layer by layer. We'll look at how the hardware helps us, then the basic software tools like locks and semaphores, and then the fancier, high-level stuff like monitors. And of course, we'll get into what happens when things go wrong, the really nasty bugs like deadlock, and we'll wrap it all up by figuring out how you choose the right tool for the job. Okay, let's start at the very beginning. What's this big, scary problem we're even trying to solve in the world of concurrent programming? Well, it's a really sneaky but incredibly dangerous bug called a race condition. The easiest way to think about this is to imagine a bunch of threads literally racing to mess with the same piece of data. The final result is basically a lottery. It completely depends on the random chance of which thread gets there first, which one gets interrupted, and who gets the last word. This leads to results that are just flat out wrong and totally unpredictable. And this is where things get really sneaky. You and I, we look at a simple line of code like count++, and we think, okay, that's one thing. But it's not. To the CPU, that's actually 3 separate instructions. It has to go fetch the value from memory and load it into a register. Then it has to add 1 to the register. And finally, it has to write that new value back to memory. Okay, and here is where it all falls apart. Just look at this timeline. At T0, the producer reads count. It's 5. Great. At T1, it calculates the new value, 6. But before it can write that back, whoops, the operating system puts it on pause. Now at T2, the consumer wakes up. It reads count, which is still 5 because the producer never got to save its work. The consumer then calculates its own result, 4. Then at T4, the producer finally gets to write its value, 6. But it's too late. At T5, the consumer wakes up and just stomps all over it. Writing 4, the final result is wrong, all because of that unlucky interruption. So all of this leads to what we formally call the critical section problem. A critical section is just any piece of your code that touches that shared data. And our entire goal is to come up with a protocol, a set of rules that all our threads have to follow to make sure only one of them is in that section at a time. Okay, pay attention here, because this is a guaranteed exam question. Any real solution to this problem has to meet 3 non-negotiable conditions. First, mutual exclusion, 1 at a time, period. Think of it like a single-person bathroom. Second, progress. If the bathroom is empty and someone's waiting, you have to let them in. You can't just keep the door locked for no reason. And third, bounded waiting. You can't have one person waiting in line forever while other people keep cutting in front of them. There has to be a fairness guarantee. So the natural question is, can't we just be clever and fix this in software? And people definitely tried. There are famous algorithms like Peterson's solution. But the thing is, on pretty much any modern machine, they just don't work. And it's the hardware's fault. See, to get every last ounce of speed, modern CPUs and compilers are constantly reordering your instructions behind your back. You might write your code thinking that you're setting X to 100 before you set a flag to true. But the hardware might look at that and say, hey, these don't depend on each other. I'll do the flag first. For a single thread, who cares? But when you've got multiple threads relying on that flag to talk to each other, boom, your logic is completely broken. And that is why we fundamentally need the hardware to help us out. We need special instructions that are guaranteed to be atomic, which is just a fancy way of saying they're uninterruptible. They have an all at once or not at all. You've got things like memory barriers, which basically tell the CPU, hey, stop reordering and finish all your work right now. And then you have the real workhorses, instructions like test and set and compare and swap. These are the bedrock that all other synchronization tools are built on. Let's really zoom in on compare and swap, or CAS, because this thing is a game changer. It's what we call an optimistic operation. It basically says, okay, I'm going to read a value. I expect it to be, say, 5. I'll go do my work to compute a new value, like 6. Then, in one single uninterruptible step, I'm going to go back and check, is the value in memory still 5? If it is, great, I'll swap my 6n. But if it's not, if someone else changed it to 7 while I was working, my swap fails, and I know I have to start over. Okay, so we've got our solid hardware foundation. Now we can climb up the ladder a bit to the tools you're probably going to use day to day, the ones provided by your operating system, locks and semaphores. Okay, another classic interview and exam question right here. What's the real difference between a mutex lock and a semaphore? A mutex is super simple. It's a key to one bathroom. It's either locked or it's unlocked. That's it. It's purely for mutual exclusion. A semaphore is more general. It's more like a whole rack of identical keys for the gym locker room. It's a counter. You can use it to control access to a pool of, say, 5 resources. Or if you set the counter to just one, it acts exactly like a mutex. Okay, now let's talk about a weird but important type of mutex, the spin lock. Normally, when a thread tries to get a lock that's taken, the OS puts it to sleep. But with a spin lock, the thread just sits in a super tight loop asking, is it free yet? Is it free yet? Is it free yet? And I know what you're thinking. That sounds incredibly wasteful, right? Just burning CPU cycles doing nothing. But here's the catch. On a multi-core machine, if the lock is only going to be held for a tiny fraction of a second, it's actually faster to just spin and wait than it is to pay the expensive cost of putting a thread to sleep and waking it back up again. So semaphores are awesome. They're super powerful, but they're also kind of dangerous. It's like juggling chainsaws. You forget one signal call or you call wait twice by accident, and you can easily create a deadlock that brings your whole program to a halt. To deal with this, some very smart people came up with a much safer, higher-level tool, the monitor. The whole magic of a monitor comes down to one word, encapsulation. It grabs your shared data and all the code that touches that data and shoves it into a protected little box. And the language itself guarantees that only one thread can be running code inside that box at any given time. The mutual exclusion is baked in, it's automatic, which means it's way, way harder for you, the programmer, to screw it up. All right, this is another one you absolutely have to know for your exam. The difference between signal on a semaphore versus a monitor. When you call signal on a semaphore, it always increments its counter. The semaphore remembers that signal happened. But a monitor's signal is more like tapping someone on the shoulder. If another thread is actually waiting on that specific condition, it wakes them up. But if no one is waiting, the signal does absolutely nothing. Poof, it's gone forever. It has no memory. Okay, so now we've got all these powerful tools. We should be safe, right? Well, not exactly. Using these tools can actually introduce a whole new category of bugs, what we call liveness failures. This is where your program looks like it's running. It hasn't crashed, but it's not actually doing anything useful. It's stuck. The most famous of these is, of course, deadlock. Let's walk through the classic example. You've got process 0. It grabs lock S, and now it needs lock Q. Simple enough. But at the exact same time, process 1 grabs lock Q, and now it needs lock S. They're stuck. They are caught in a deadly embrace. P0 won't release S until it gets Q, and P1 won't release Q until it gets S. They will wait forever. Okay, deadlock is pretty obvious once you see it, but this next one, priority inversion, is way more sneaky and, honestly, kind of absurd. Check this out. At time 1, a low priority task, L, grabs a lock. Then a high priority task, H, comes along and needs that same lock. So naturally, H has to wait for L to finish. But here's where it gets crazy. A medium priority task, M, that has nothing to do with the lock becomes ready to run. The scheduler sees that M is more important than L, so it boots L off the CPU. The result is just nuts. The most important task, H, is now effectively blocked by a medium importance task, M. And hey, if you think this is just some weird problem for a textbook, you are dead wrong. This actually happened on Mars. The Pathfinder rover kept mysteriously rebooting over and over. And after days of frantic debugging, the engineers at NASA figured out it was this exact problem. A high-priority communications task was being starved by a medium-priority weather task. They had to fix it by uploading a patch from millions of miles away. All right, we've covered a ton of ground. The tools, the scary things that can go wrong. Let's put it all together and figure out how to be a smart developer. You have to know which tool to pick from your toolbox. And a lot of the time, the choice comes down to one key factor: contention. And contention is really just a simple idea. How many threads are trying to get the same lock at the same time? So look, the takeaway here is pretty clear. When you don't have a lot of threads fighting over a resource, low or moderate contention, that optimistic compare and swap approach is way faster. You avoid all the heavy costs of putting threads to sleep. But when the fight gets intense, when you have high contention, all those optimistic CAS operations start failing and retrying over and over. And suddenly, it's much more efficient to just use a traditional lock and have waiting threads take a nap. So I want to leave you with a challenge, something to chew on. You've seen the whole ladder now, from the raw atomic instructions on the CPU all the way up to high-level monitors. The absolute cutting edge of high-performance computing is in building lock-free data structures. So the real question, the one that separates the pros, is how would you use something powerful like compare and swap to build something like a queue or a stack that doesn't use any locks at all? That's where the mastery really begins.